morning, everyone. Thank you for joining us today for another deep dive.
Good morning. Great to be here.
In our last deep dive,
Yeah.
we really got a handle on real-world applications and case studies of the Internet of Things. Saw how it's already woven into so much of our lives.
Yeah, it really set the stage, didn't it? Seeing the practical side of things.
Yeah, exactly. And today, we're going even further. We're peering into the looking glass, really, to explore the future of Internet of Things. This is actually our final deep dive in this foundational IoT series, and we're hoping to really connect some important dots today.
It feels like a fitting culmination, absolutely, because the IoT we see today, as remarkable as it is in many ways, it's really just the opening act.
Just scratching the surface?
Pretty much. We're, I think, genuinely on the cusp of a future where the fusion of the digital and physical worlds becomes, well, so seamless, so intelligent, and so pervasive. It's going to fundamentally redefine how we live and interact with, well, everything around us.
I couldn't agree more. And it's such a huge topic, the future, right? So to make sure we really unpack it properly, we've framed today's session as a comprehensive Q&A.
Good plan. Keeps us focused.
Yeah, hopefully. So for clarity, what we'll do is first present a roadmap of all the core questions we plan to cover.
All right.
And then we'll just tackle them one by one sequentially. How does that sound?
It's like a solid approach. Lay it all out first.
Okay, great. So here's the roadmap of questions we'll be exploring today. 1. What will be the major leap in capability from today's 5G networks to the 6G networks of tomorrow? 2. How will 6G's capabilities, particularly its integrated sensing, enable new IoT applications? 3. Beyond connectivity, what is the artificial intelligence of things, or AIoT, and how does it evolve from the edge AI we've discussed previously? 4. How can a fleet of devices learn collectively without sharing their raw, private data? 5. We've touched on digital twins before. How is this concept expected to expand in the future? 6. Can you provide a specific example how a large-scale digital twin could be used? 7. The proliferation of billions of devices raises environmental concerns. What is sustainable IoT or green IoT? 8. What are some of the key hardware innovations that can make IoT more sustainable? 9. For those looking to build this future, what are some of the in-demand career paths in IoT? 10. You mentioned the IoT Solutions Architect. What does that role entail? 11. For those in academia or R&D, what are some of the research frontiers in next-generation security for IoT? 12. What about research into novel sensor technologies? 13. As our environment becomes saturated with devices, what new forms of human-IoT interaction are being researched? And final number 14. As we conclude our 10-part series, what is the ultimate message about the future of the Internet of Things?
That's quite a list. Covers a lot of ground.
It does, doesn't it?
Yeah.
But I think hitting each of these will give us a really solid picture of where things are heading.
Agreed. Let's dive in.
All right. So let's kick things off with that foundational layer, starting logically with connectivity. We've all gotten pretty accustomed to 5G now, haven't we? But what's the actual leap we can expect going from today's 5G networks to the 6G networks of tomorrow? What really makes 6G different beyond just being, faster?
That's an excellent way to frame it, because when we talk about 6G, it really isn't just about a higher number on the box. It's aiming to be a genuine paradigm shift.
Okay.
So yes, speed is part of it. While 5G pushed us into, gigabit per second speeds, which felt revolutionary not long ago.
Still feels pretty fast.
It does. But 6G is projected to hit theoretical speeds in the terabits per second range.
Terabits. So that's, what, 1,000 times faster than gigabits?
Potentially, yes. 1,000 times faster. But here's I think, the real insight, the crucial point. It's not just speed for speed's sake. The latency. That's the delay in communication, the round-trip time.
Right, the lag.
Exactly, the lag. That's expected to plummet down to microsecond levels.
Microsecond, not millisecond.
Microsecond. We're talking orders of magnitude lower than even the best 5G low-latency capabilities.
Whoa. Okay, so what does that actually mean for you, for applications? 1,000 times faster and microsecond latency?
Well, think about it. Imagine.
Yeah.
Imagine a surgeon performing a really complex, delicate operation remotely, maybe on the other side of the world.
Okay.
With microsecond latency, they could potentially feel every subtle resistance, every tremor through their robotic instruments, almost as if they were physically present in the operating room. The feedback loop is virtually instantaneous.
But it removes that barrier of distance in a truly tactile way.
Precisely. That's the kind of mind-bending implication we're talking about with 6G's potential. It's this combination, terabit speeds and microsecond latency, that really lays the foundation for a truly seamless, real-time fusion of our digital and physical worlds. It's fundamental.
That really puts it in perspective. The microsecond latency.
Yeah.
It just opens up a whole new realm of possibilities. It sounds like it transcends mere communication, like you said.
It really does.
So if 6G is moving beyond just, faster data downloads, how will its other capabilities, particularly this integrated sensing you hinted at, how will that enable truly new IoT applications, things we can maybe barely conceive of today?
Yes, the sensing aspect. This is where I think it gets genuinely revolutionary. Perhaps the most profound ambition of 6G is this idea of merging communication with sensing.
Merging them?
The network itself evolves into a giant, pervasive sensor. It wouldn't just carry data, it would use its own radio waves actively, or perhaps passively analyze reflections, to precisely detect the location, the movement, even the shape and maybe material properties of objects within its coverage.
So the network itself is mapping the physical world.
In essence, yes. Think of it as creating a real-time, high-fidelity, dynamic map of the physical environment around us. Passively, continuously, just as a byproduct of the network operating.
Okay, that capability changes everything for IoT, doesn't it?
It really does. Combine that pervasive sensing with the microsecond latency we just talked about.
Right.
And suddenly that remote robotic surgery scenario, it becomes even more feasible, especially with rich haptic feedback. That's the tactile sensation, allowing the surgeon to feel the tissue they're working on. It makes the remote experience incredibly realistic.
That feeling component is key.
Absolutely. And beyond surgery, the network's integrated sensing could potentially eliminate the need for some dedicated physical sensors altogether.
Really? Like
Yeah.
what?
Well, imagine the 6G signal itself monitoring traffic flow on a highway without needing cameras or road sensors, or detecting subtle structural vibrations in a bridge to predict maintenance needs, or even monitoring the health and operation of machinery in a factory just by analyzing how the radio waves interact with them.
So it reduces the clutter of physical sensors potentially.
It could, yes. And think about immersive experiences. Truly convincing extended reality, or XR, virtual and augmented reality combined. Holographic telepresence where the other person feels genuinely there in the room with you.
That requires incredible bandwidth and low latency.
Exactly. And coordinating massive swarms, hundreds, thousands of autonomous drones or vehicles. That needs near-perfect synchronization, which microsecond latency and high bandwidth enable. 6G sensing could help them navigate and interact with the physical world with unprecedented precision.
The idea of the network itself becoming a sensor is, genuinely transformative. It feels like the environment itself is gaining a form of perception.
That's a good way to put it, a perceptive environment.
Okay, let's shift gears slightly. We've talked about connectivity, now intelligence. We've discussed Edge AI before in this series, AI computation happening closer to the data source on the device or nearby. How does this idea of artificial intelligence of things, or AIoT, evolve from that? Is it just a rebranding or something more? You mentioned creating something truly. Well, the word you used was sentient. That's a strong word.
It is a strong word, and maybe slightly hyperbolic, but it captures the ambition, I think. AIoT isn't just a rebranding of Edge AI. While Edge AI is primarily about deploying pre-trained AI models at the edge, for faster inference or offline operation.
And running the AI locally.
Exactly. AIoT represents something much deeper, a more pervasive fusion of AI across the entire IoT stack, from the tiniest sensor gathering raw data through the edge gateways all the way up to the global cloud infrastructure.
So AI isn't just at the edge, it's everywhere.
That's the vision. The ambition isn't just having devices that can run AI algorithms. It's about creating a truly sentient-like responsive network where intelligence isn't bottlenecked in the cloud or just running static models at the edge. It's distributed everywhere.
Okay, distributed intelligence. But what's the fundamental shift from edge AI executing models to this AIoT vision?
The shift is really from devices simply executing pre-trained instructions or models to devices that can actively learn, reason, and adapt, often collectively, based on the data they perceive and share.
Collectively.
Yes. It's about enabling distributed, almost emergent intelligence. The system as a whole, the network of devices, becomes smarter, more adaptive, more capable than the sum of its individual parts because they're learning together.
That concept of devices learning collectively is really powerful, especially when you think about the sheer volume and often the sensitive nature of the data these devices collect. Which brings us neatly to the next question. How can a vast fleet of devices, maybe millions or billions, actually learn together and build that collective intelligence without sharing all their raw, often very private data? That seems like a massive privacy hurdle.
It absolutely is a hurdle, probably the major hurdle for realizing that vision of collective learning. And that's precisely where techniques like federated learning become not just interesting, but really indispensable.
Federated learning, we've touched on that, but can you break down how it works in this context?
Sure. So with federated learning, the basic idea is this. Each individual device, say your smartphone or a sensor in a factory or a connected car, trains an AI model using its own local data that stays right there on the device.
Okay, so my personal data, my photos, my driving habits, whatever it is, stays put.
Exactly. It doesn't get uploaded to some central server. Instead of sending the raw data, the device only shares its learnings. These are essentially the updated parameters, or the changes, to its local AI model that resulted from training on its private data.
Just the insights, not the data itself.
Precisely. And typically these shared learnings, these model updates, are also processed to enhance privacy, further maybe encrypted or anonymized, using techniques like differential privacy.
Okay, so it sends these protected learnings where?
They're sent to a central coordination server, or sometimes managed through a more distributed peer-to-peer mechanism. This central coordinator then aggregates all these individual learnings from many, many devices.
Mixes them all together.
It intelligently combines them, yes, to update a shared global AI model. This improved global model is then sent back down to the individual devices, so they all benefit from the collective experience and intelligence without anyone having exposed their private, raw information.
Got it. So each device contributes its little piece of wisdom, basically,
Yeah.
to make the whole system smarter, but without revealing the secrets behind that wisdom.
That's a great analogy. It allows for powerful collective intelligence to be built, making the services we use smarter and more personalized, but in a way that's designed from the ground up to protect individual privacy. It's a really crucial piece of the puzzle for trustworthy AIoT.
Federated learning really seems like a clever way to solve that fundamental privacy challenge. Collective intelligence without collective data exposure.
Exactly.
And speaking of creating these intelligent distributed systems, that leads us perfectly into the evolution of another concept we've discussed, digital twins. We've talked about them before as essentially a virtual replica of a physical asset like a wind turbine or a jet engine. How is this concept expected to expand in the future? Is it just more twins of more objects? Or is it evolving beyond replicating individual things?
Oh, it's definitely evolving.
Yeah.
What's truly fascinating here is the massive expansion in scope and complexity we're going to see with digital twins. They're moving significantly beyond just replicating single isolated objects.
Okay, so bigger scale.
Much bigger scale. We're talking about modeling entire complex, interconnected systems, creating these high-fidelity, dynamic simulations of vast parts of our world.
Like what kinds of systems?
Think about it. We're moving beyond just having a digital twin of a single jet engine. The next generation aims to model the entire aircraft that engine is part of.
Right.
Then maybe the entire fleet of aircraft operated by an airline, and potentially even the air traffic control system that the fleet operates within, each level interacting with the others.
Wow, that's layers upon layers of complexity.
Exactly. And we'll see this across industries. Digital twins for entire factories, modeling every machine, process, and workflow. Twins of incredibly complex global supply chains, tracking goods and predicting disruptions. Twins of national power grids, optimizing energy flow and predicting faults.
That's like a simulation of reality almost.
Getting closer to it. And perhaps one of the most profound areas is applying this to human biological systems.
Digital twins.
Of people. Essentially, yes. Imagine a highly personalized digital twin of a patient. It could be built from their genomic data, real-time information from wearable sensors, their medical history, imaging scans, a comprehensive virtual model.
And what would doctors do with that?
They could use this patient digital twin to simulate the effects of different drugs, different dosages, or even complex surgical procedures before they're ever administered to the actual patient. They could test hypotheses, predict outcomes, and find the most effective personalized therapy with potentially fewer side effects.
That's incredible. It shifts digital twins from just being diagnostic tools for machines to being predictive and prescriptive tools for, well, for human health.
Precisely. It's about moving towards truly personalized predictive medicine. The potential impact is enormous.
Okay, that personalized medicine example is incredibly powerful. But sticking with the larger scale for a moment, can you give us another concrete, specific example, something maybe more infrastructure-focused, of how a really large-scale digital twin could be used in a real-world scenario, something we can really visualize?
Certainly. Let's consider city planning. Imagine a city creating a comprehensive, dynamic digital twin of its entire metropolitan area.
A twin of the whole city.
Yes. This twin wouldn't be static. It would be constantly fed with real-time IoT data streams. Think data from traffic sensors, air quality monitors, public transport usage, energy consumption in buildings, pedestrian flow, all flowing into this unified virtual model.
Okay, a living model of the city. Then what?
Then, city planners could use this incredibly rich dynamic model to simulate the precise impact of major decisions before they make them. For instance, what happens if we build a new subway line here? They could run the simulation and see the projected effects on traffic patterns across the city, changes in air pollution levels in specific neighborhoods, maybe even predict the impact on economic activity in different districts.
So they can test drive policies virtually.
Exactly. They can run countless what-if scenarios. What if we change traffic light timings? What if we introduce a congestion charge? What if there's a major event? They can optimize plans, anticipate unintended consequences, and make complex, data-driven decisions that affect millions of people, all based on simulating the outcomes first.
That seems invaluable for managing complex urban environments.
It really does. Or think about logistics. A major global logistics company could have a digital twin of its entire supply chain ships. Planes, trucks, warehouses, inventory levels, everything. Now imagine a port suddenly closes due to a storm or some geopolitical event. The digital twin, analyzing real-time data and potential knock-on effects, could instantly predict the cascading disruption across the entire network.
And
then, potentially, the system could use AI running on the digital twin to autonomously figure out the best way to reroute hundreds, maybe thousands of shipments, calculating alternative routes, transport modes, considering costs and delivery times, all to minimize the disruption and keep goods flowing as efficiently as possible. It shows the optimal path forward in near real time.
That predictive and almost prescriptive power of these large-scale twins is, truly remarkable. They seem like essential tools for navigating the complexity of the modern world.
I think they will be, increasingly so.
But let's pivot slightly, because creating all this infrastructure, all these twins, relies on deploying billions, potentially trillions of connected devices eventually. And that naturally raises some pretty serious environmental concerns.
Yeah, absolutely. It's a critical consideration.
So what exactly is sustainable IoT or green IoT, and why is it becoming so crucial as we look towards this massive expansion?
It's a fundamentally important question, you're right, because building this connected future responsibly means we absolutely have to address the environmental footprint head-on. Sustainable IoT, or sometimes called green IoT, is essentially the movement to directly confront these environmental challenges.
Challenges like?
Well, the two big ones are energy consumption. These billions of devices, plus the networks and data centers supporting them, consume a vast amount of energy throughout their life cycle, from manufacturing to operation to disposal. And secondly, electronic waste, or e-waste. We risk creating mountains of discarded devices if they're not designed with end of life in mind.
Okay, energy and waste. So how does green IoT tackle this?
It really operates on two crucial fronts. First, it's about making the IoT technology itself inherently more sustainable. That means focusing on energy efficiency in hardware and software, using greener materials, designing for longevity and recyclability, and minimizing waste during manufacturing.
Making the tech greener.
Exactly. But the second front is equally vital and perhaps even more impactful in the long run. It's about leveraging IoT as a powerful tool to help solve broader environmental problems.
Using IoT for sustainability.
Precisely. Think about using sensor networks for precision agriculture to optimize water and fertilizer use, drastically reducing waste and runoff, or smart building systems that minimize energy consumption for heating, cooling, and lighting, or intelligent waste management systems that optimize collection routes and improve recycling rates. IoT can be a key enabler for a more sustainable economy across many sectors.
That's a critical dual approach. Clean up IoT's own act and use it as a tool for global good.
That's the essence of it, yes.
So focusing specifically on that first front, making the IoT technology itself inherently more sustainable, what are some of the key hardware innovations that can really drive this green IoT forward? What's happening on the physical device level?
Yeah, the future of IoT hardware is undeniably looking greener, out of necessity as much as anything else. A really major frontier for innovation is the development of biodegradable electronics.
Electronics that decompose?
Essentially, yes. Components, sensors, even potentially entire simple devices made from organic materials or other compounds that can safely break down in the environment at the end of their useful life. This could drastically reduce the accumulation of persistent e-waste, especially for applications where devices might be widely dispersed or hard to collect.
That sounds almost like science fiction, but okay, biodegradable components. What else?
Perhaps the area with the most potentially widespread impact is energy harvesting.
Right. You mentioned self-powered sensors earlier.
Exactly. This is about creating sensors and simple devices that are entirely self-powered. They draw the minuscule amounts of energy they need directly from their surrounding environment.
From where? What ambient sources?
All sorts. Tiny solar cells scavenging indoor or outdoor light. Piezoelectric materials generating power from vibrations. Imagine a sensor on a machine powered by the machine's own hum. Thermoelectric generators using heat differences. Perhaps the waste heat from electronics or industrial processes. Even harvesting energy from the ubiquitous radio waves already filling our airwaves from Wi-Fi, TV broadcasts, mobile signals.
Harvesting energy from thin air, almost.
Sounds like it, doesn't it? But the energy levels are tiny, suitable only for very low-power devices. But the key is eliminating the need for batteries in potentially billions, maybe trillions of deployed devices.
And the impact of eliminating batteries would be?
Huge. Firstly, it slashes maintenance costs, no need to replace batteries and sensors hidden in walls or scattered across fields. But more importantly, from a green perspective, it massively reduces the manufacturing footprint and the disposal problem associated with batteries, many of which contain toxic materials. That's where the really significant sustainability gain comes from battery-free operation.
That would be absolutely revolutionary. Self-powered devices just blending into the environment, doing their job without needing battery changes or contributing to that waste stream. It's hard to overstate the impact that could have.
It really is a game changer for deploying IoT sustainably at massive scale.
Okay. So as we talk about building this incredible, sustainable, intelligent future, let's think about the people involved. For those listening who are maybe students or engineers or tech enthusiasts looking to contribute to this field, what are some of the most in-demand career paths in IoT today and looking forward? Where should someone focus their skills if they want to be part of this?
That's a great question because the exponential growth of IoT is definitely creating a massive and constantly evolving demand for skilled professionals across the board. It's a highly interdisciplinary field, as you can imagine.
It touches everything.
It really does. It draws heavily from software engineering, hardware design, data science, networking, cybersecurity. The list goes on. But if we were to pinpoint some of the most critical, consistently in-demand career paths right now, and likely for the foreseeable future.
Yeah, what are the hot roles?
Well, first, there's the IoT Solutions Architect. We can talk more about them, but they're the big picture designers. Then you have the IoT Embedded Systems Developer. These are the folks working hands-on with the microcontrollers, the firmware, the actual device hardware.
The ones making the things smart.
Exactly. Then, critically important, is the IoT Cloud Engineer, or Cloud Architect. They focus on building and managing the back-end infrastructure, the platforms that ingest, store, process, and analyze all that data coming from the devices, often involving major cloud providers.
Handling the data deluge.
Absolutely, which leads directly to the IoT Data Scientist, or AI Specialist. Their job is to make sense of that deluge, to extract meaningful, actionable insights from the immense data flows using machine learning and analytics techniques.
Finding the value in the data.
Precisely. And last, but certainly not least, maybe increasingly most importantly, is the IoT Security Specialist. Given the expanded attack surface with billions of connected devices, their role in designing, implementing, and managing security measures to safeguard these complex interconnected networks from threats is absolutely crucial.
Security has to be baked in from the start.
It absolutely must be. It can't be an afterthought in IoT.
That's a fantastic overview of the professional landscape. Let's maybe double-click on one of those roles you mentioned first, the IoT Solutions Architect. What exactly does that role entail day to day? It sounds like a really pivotal big picture position that requires a unique blend of skills.
It truly is the big picture role. Yeah. You could almost think of them as the orchestra conductor for an IoT project. An IoT Solutions Architect is fundamentally responsible for designing the entire end-to-end IoT system.
End-to-end, meaning
from the sensors and devices at the edge, all the way through the network connectivity, the cloud platform, the data processing, the analytics, and how it integrates with existing business systems or delivers value to the end user.
So they need to understand all the pieces.
Deeply. This isn't just about picking a specific sensor off a shelf or choosing a cloud vendor. It involves making really strategic choices about, well, what are are the right sensors for this specific problem? What capabilities do they need? What communication protocols make sense? Is it short range like Wi-Fi or Bluetooth, long range like LoRaWAN or NB-IoT, or cellular like 5G? Each has trade-offs in power, range, bandwidth, cost.
So selecting the tech stack.
Yes, but also designing the overall cloud architecture. How will data be ingested reliably? How will it be stored efficiently? How will it be processed in real-time streams or batch analysis? What analytics tools are needed? They also need to plan the entire data analytics strategy. What insights are we trying to get, and how will the system deliver them?
Sounds incredibly complex.
It is. Their ultimate goal is to ensure all these diverse technological pieces, hardware, software, networking, cloud, AI, work together seamlessly, securely, and reliably to solve a specific business problem or meet a user need. They ensure the entire solution is cohesive, scalable for future growth, cost-effective, and genuinely effective at achieving its objective.
So they need deep technical knowledge, but also a strong understanding of the business context.
Absolutely critical. They need to translate business requirements into technical specifications and vice versa. They bridge the gap between the technology and the business value.
Fascinating role. What would you say is the biggest challenge they typically face, trying to harmonize all those different technologies and business needs?
That's a great question. I think one of the perennial biggest challenges is often interoperability. Getting devices, communication protocols, platforms, and software components, often from different vendors with different standards, to actually talk to each other effectively and securely. It sounds simple, but it can be incredibly complex in practice.
Stitching it all together.
Exactly. And beyond that, there's the constant balancing act. They have to balance technical requirements, performance, features, reliability with practical constraints like cost, development time, and ease of deployment and maintenance. And crucially, they need to ensure robust security and privacy considerations are designed in from the very beginning, not bolted on later. Designing a system that not only works now, but can also evolve and adapt as new technologies emerge and business needs inevitably shift. That's the core challenge.
A constant juggling act. Okay, shifting focus again. For those perhaps in academia or research and development labs, what are some of the really cutting-edge research frontiers in next-generation security for IoT? Especially thinking about the future threats posed by things like quantum computing or just the sheer scale of deployment.
Security is absolutely paramount for the future of IoT, and yes, it's a constantly evolving arms race. Research is pushing hard on several fronts. One hugely critical area is developing and standardizing post-quantum cryptography, or PQC.
Post-quantum, meaning secure against quantum computers.
Precisely. The immense processing power promised by future, large-scale quantum computers poses a direct existential threat to the public key encryption methods we rely on today for almost everything: secure websites, financial transactions, software updates, private communications. Algorithms like RSA or ECC could potentially be broken relatively easily.
That could be catastrophic.
Utterly. So researchers worldwide are racing to develop entirely new cryptographic algorithms based on different mathematical problems that are believed to be resistant to attacks from both classical and quantum computers. Transitioning our global digital infrastructure, including IoT systems, to PQC is going to be a massive, essential undertaking over the next decade or two.
So future-proofing security against a quantum threat. What else?
Another incredibly important and active area of research is around decentralized identity or self-sovereign identity.
The decentralized identity. What's the core idea?
The core idea is to move away from relying on centralized authorities like governments or large corporations to issue and manage our digital identities. Instead, it explores using technologies like blockchain or other distributed ledger technologies, DLTs, to give individual users and even devices themselves far more direct control over their own digital identities and the data associated with them.
So I control my own identity data.
That's the goal. You could have a portable, secure digital wallet holding verifiable credentials, and you choose exactly what information to share with whom and for what purpose, without needing a central intermediary to broker that trust or hold all the data. For IoT, this could revolutionize how devices authenticate themselves, how access permissions are granted, and how trust is established in these vast distributed networks without single points of failure or control.
That sounds like a fundamental rethinking of digital trust and identity online.
It really is. It aims to make identity more user-centric, more secure, and more privacy-preserving, which is vital for a world saturated with connected devices.
It's incredible to think the future of security involves preparing for quantum computers and completely rethinking digital identity. Very cool stuff.
Definitely cutting edge.
Now, beyond security, what about research into novel sensor technologies themselves? What new kinds of sensors are bubbling up in labs, pushing the boundaries of what we can actually detect or measure in the physical world?
Oh, the frontier of sensor research is incredibly exciting. It's really pushing the boundaries of miniaturization, sensitivity, and capability. One major focus is on developing nanoscale sensors.
Nano, so incredibly tiny.
Incredibly tiny. Devices operating at the molecular or even atomic level. This opens up possibilities for detecting minute traces of chemicals, pollutants, or biological markers with unprecedented sensitivity.
Applications for that.
Huge potential in environmental monitoring, medical diagnostics, industrial process control. Then there's a significant push towards biocompatible sensors. These are sensors designed to be safely used inside the human body.
Inside the body. Wow.
Yes, for things like continuous hyper-personalized health monitoring, tracking blood glucose, specific proteins, or other biomarkers in real time. Or enabling highly targeted drug delivery systems that release medication only when and where it's needed based on sensor readings. Or even interfacing directly with the nervous system.
That's blurring the lines between technology and biology.
It really is. Another fascinating, though perhaps further out area is the concept of smart dust.
Smart dust. Sounds intriguing.
It refers to the idea of developing vast numbers of tiny autonomous sensor nodes, maybe no larger than a grain of sand or even smaller. These modes could potentially be scattered or sprayed into an environment like across a field or within the structure of a building or even in the atmosphere.
And they just collect data.
Yes. Collectively forming a massive distributed sensor network. They could monitor environmental conditions, structural integrity, track assets, perhaps even perform surveillance, all on an unprecedented scale of distribution and granularity. There are huge technical challenges, of course, power, communication, deployment, but the concept is powerful.
Like an invisible sensing cloud.
Something like that. And underpinning all of this, naturally, is continuous research into new materials for a more sensitive detection, materials that are more biocompatible, and crucially, as we discussed earlier, new materials for ever more efficient energy harvesting, allowing these tiny, numerous sensors to truly be self-powered and maintenance-free for long periods.
The material science is key.
Absolutely fundamental.
Okay, smart dust really paints a picture of a future with pervasive, almost invisible sensing capabilities. Which leads to a really interesting question. As our environment becomes increasingly saturated with potentially billions, maybe even trillions, of these smart devices, how will we as humans interact with them all? What new forms of human IoT interaction are being researched? Surely we can't just use smartphone apps for everything, right?
That's exactly right. The current modes of interaction, primarily screens and basic voice commands, simply won't scale effectively or feel natural in a world densely populated with smart, interconnected objects and environments. Research in human IoT interaction, sometimes called H-IoT, is actively exploring interfaces that go far beyond our current paradigms.
Like what? What's beyond screens and saying, hey, Google?
Well, one promising area is advanced gesture control. Imagine using intuitive hand movements or even subtle body postures to naturally control smart devices in your home, your car, or your workplace. Waving to dim the lights, pointing to transfer a file, maybe specific postures indicating your availability or focus level to the environment.
More intuitive physical interaction.
Exactly, making the interaction feel more embodied and less mediated by a specific device. Another huge area is augmented reality, AR overlays.
AR glasses and things.
Precisely. Imagine wearing lightweight AR glasses where relevant digital information and controls are displayed directly overlaid onto your view of the physical world. You could look at a malfunctioning machine and see diagnostic data superimposed on it, or look at a smart thermostat and adjust it with a glance or a gesture. It creates this seamless blend where you interact with digital information in context.
Bringing the data into the real world visually.
Exactly. And then, perhaps the most profound and certainly the most futuristic sounding area is research into direct brain-computer interfaces, or BCIs.
Controlling things with your mind.
That's the ultimate potential, yes.
Yeah.
BCIs aim to read brain signals either non-invasively using scalp sensors or potentially through more invasive implants in the longer term, and translate those signals into commands for external devices or systems.
So you could think about turning on the lights, and they turn on.
Potentially, yes. Or control a prosthetic limb, navigate a complex software interface, or even communicate just through thought. There are enormous technical and ethical challenges, of course, but the research is progressing rapidly. The idea is to create the ultimate seamless interface, blurring the lines between our intentions and their digital or physical execution in the environment.
Wow. Gesture, AR, BCIs.
Yeah.
It really suggests a future where our interaction with technology becomes much more integrated into our physical being and our perception of the world.
That's the direction it seems to be heading, towards more natural, contextual, and perhaps even subconscious interaction.
Okay. We've covered a tremendous amount of ground: 6G connectivity, the rise of AIoT and collective learning, the expansion of digital twins, the critical need for sustainability, evolving career paths, next-gen security, novel sensors, and new interaction paradigms.
Yeah.
As we bring this deep dive, and indeed this entire 10-part series on IoT, to a close, what is the ultimate message? If you had to distill it down, what's the key takeaway about the future of the Internet of Things that our listeners should really hold on to?
That's the big question, isn't it? If we try to connect all these powerful threads we've discussed today, and really throughout the whole series, I think the ultimate message is this. The Internet of Things isn't just, a collection of neat connected gadgets or industrial sensors. It represents one of the most profound technological transformations of our time. It's poised to become something akin to the central nervous system of our planet.
A planetary nervous system.
It sounds grand, but consider the potential. Its future, as we've seen, will likely be defined by this incredibly powerful and synergistic convergence. The near-instantaneous sensing-capable connectivity of 6G, feeding the distributed cognition and collective learning capabilities of AIoT, which in turn powers the predictive and prescriptive insights from large-scale, complex digital twins. And all of this absolutely must be built upon the crucial, non-negotiable foundation of sustainability and green IoT principles.
These forces multiplying each other.
Exactly. This path forward, this convergence, presents absolutely immense opportunity. It will demand new skills, it will foster incredible innovation, it will undoubtedly create entirely new industries we can't even fully envision yet. However, and this is critical, this future isn't some predetermined outcome. It isn't guaranteed. It must be built with profound intention. Meaning we have to be deliberate. The technical challenges achieving that scale, ensuring robust security, solving interoperability are significant, yes, but they are arguably matched or even surpassed by the critical need to proactively consider and address the ethical and societal implications. Issues of governance, ensuring equitable access so the benefits aren't concentrated, safeguarding privacy in an increasingly sensed world, these need to be central to the design process.
Technology and ethics hand in hand.
They have to be. Ultimately, the true promise of IoT, I believe, isn't just about creating a world that is merely more automated or more efficient, though it can certainly do that. The deeper promise is to help create a world that is more responsive to genuine human needs, more efficient and respectful in its use of our planet's precious resources, and perhaps more resilient in the face of the complex global challenges we face, from pandemics to climate change. Our greatest task, really, as engineers, as innovators, as policymakers, as citizens, is to work together to imbue this incredibly powerful emerging technology with our collective wisdom and foresight.
That's a truly powerful and, I think, essential thought to end on. Building this future with wisdom and intention, consciously addressing both the immense technical possibilities and the equally significant societal responsibilities. It really underscores that the Internet of Things isn't just about connecting devices. It's fundamentally about shaping a more intelligent, more efficient, and hopefully, ultimately, a more human-centered world.
Exactly. And it's a journey, as we said at the start, that we've truly just begun. The possibilities ahead are almost limitless, but so are the responsibilities that come with them.
What an incredible journey it's been throughout this entire series.
Yeah.
We sincerely hope that all of you listening have found these deep dives into the many facets of the Internet of Things as enlightening and maybe as thought-provoking as we have.
It's been fascinating to explore it from so many angles.
It really has. And as we officially wrap up this IoT series, we're genuinely thrilled to announce our upcoming new series. We'll be embarking on another fascinating exploration into a different but equally transformative field. Fundamentals of nanotechnology.
The world of the very small.
Exactly. We'll delve into the incredible science and engineering happening at the nanoscale, the realm of atoms and molecules, and explore its massive implications for pretty much everything, from medicine and material science to computing and energy.
That promises to be another absolutely captivating exploration. Nanotechnology is underpinning so many future advancements.
We think so too. So thank you once again for joining us today and for sticking with us throughout this entire IoT series. We truly appreciate your engagement and your curiosity. Please be sure to subscribe to our channel, Tech AI and Beyond, so you don't miss the start of the nanotechnology series or any of our future deep dives into the technologies that are shaping our world.
Thanks, everyone.
We'll catch you next time.